We are Group 3 of the System ID and Controls Lab with Emma Bibbings, Tyler Seifert, Aidan McGannon, Kevin Rubio, and Nick Borcelli. Quanser Incorporated has developed a direct current electric motor and would like Burdell Incorporated to create a controller for the motor so that it can be used for positioning. Burdell has not been provided with the exact electrical or mechanical specifications for the DC motor, but has been provided the general motor with unknown parameters for the DC motor. It is up to us to determine the parameters for the DC motor model, to describe the provided Quanser motor, and to create a PID controller for the DC motor to allow for position control. Before the PID controller can be set up, we need to identify the constants of the system, motor constant Km and time constant Tm. To do this, we must first consider the angular speed control. This lab is broken up into 3 main areas. Using LabVIEW, we begin with system nonlinearity by determining the motor dead zone. Next, we move on to the time domain system identification, where we determine the time domain ID using a step input, and next we investigate the increased inertia. Finally, with the frequency domain identification, we find the input and output amplitude and phase difference at each frequency.
Now we will discuss the nonlinearity of our system. As shown in the figure and table, as the voltage input increases, the steady-state velocity also increases. Figure 5 shows the voltage and steady-state velocity relationship. The dead zone, which is defined as the region at which the velocity is 0 for some positive voltage, has limits of 0 to 0.5 volts. The saturation zone is defined at the region at which the linear relationship of steady-state velocity being equal to Km times the input voltage does not apply, and in this case is any voltage greater than 8 volts. The input voltage is limited by the circuitry internal to the motor in order to protect its circuit components. The linear regime is defined as a region in which the previously mentioned linear relationship is applicable, and in this case is bounds of 0.5 to 6 volts.
So in part 2 is the time domain system identification. Here we have our Km and Tm values varying with voltage inputs, and Km is the motor gain constant, Tm is the motor time constant, and you can see Km increases and Tm decreases as voltage increases, with some variation, especially in the lower voltage region. Both of these values are probably most affected by friction. In these lower voltages, there's lower speeds, and so it takes longer to reach the point, and there's just problems with overcoming static frictions that the model assumes does not exist. And this can cause problems when determining these values.
Thanks, Nick, for explaining that. Onwards, let us observe how Km and Tm should remain constant throughout the linear regimen. The procedure is quite simple. Plot steady-state angular velocity as on the y versus input voltages on the x. You will then be able to identify a linear region excluding the saturation zone and dead zone, and therefore can extract Km from the slope. And Tm, which is just the average of all individual Tm values at each input voltage, can also be extracted from the plot. Moreover, you can use the equation listed on the slide, where the angular velocity is equal to Vm times Km times 1 minus e to the power of negative t over Tm, where t is time. Looking further into the steady state response, it can be noted that noise is indeed present. However, it is settled and will continue to follow a repeated path until it meets the saturation zone. Moreover, comparing our experimental step response to our theoretical step response plots, it's evident that the experimental outputs sinusoidal data, as opposed to the theoretical outputting a regular set of connected data points. Let us now investigate the effects that inertia has on Km and Tm values. We can demonstrate the effects by adding a weight. If the Km formula is analyzed, it can be noted that there is no inertial term included, which is represented by the variable j, therefore making Km independent from inertial effects. This ultimately results into steady-state angular velocities remaining the same. However, Tm's formula is proportional and dependent on the inertial value, so the change we see in the increased values from unweighted to weighted is accurate and expected. Well, what does this all mean? Well, the object will accelerate slower, yet will reach the same steady-state angular velocity as it would if it was unweighted, as noted in the figure on the slide. Now, if you are unfamiliar with the variables below that we have not yet mentioned, allow me to define. Ra is the resistor resistance, B is the damper constant, Kt is the motor torque constant, while Kb is the back EMF constant.
Now we are going to talk about the frequency domain results and discuss the implications of our findings. The result for the frequency analysis we see here is expected because physical systems often represent low-pass filters, which is seen in this Bode plot. This is because physical systems have inertia and momentum, and these properties can't be changed instantaneously. Therefore, at higher frequencies, the gain of these systems begins to fall off as a result of the output not being able to change as fast as the input. From the Bode plots, we can solve for the cutoff frequency, omega c, by finding the frequency that coincides with a gain of -3 decibels from the gain at 0 radians per second. This frequency also coincides with a phase lag of 45 degrees. By using this cutoff frequency, we can then solve for the time constant Tm. Km is calculated by finding the limit of the gain as omega approaches 0, and then converting this from decibels to a regular magnitude. The difference between the constants found from the time domain analysis and the frequency domain analysis arise from the simplifying assumptions we made for our model. These assumptions include assuming that friction is negligible and inductance can be ignored. These assumptions have a much smaller effect on the time domain analysis because the system eventually reaches steady state, so assumptions such as the inductance being 0 are valid. In this case, however, the system never reaches steady state because the input is a sinusoidal wave. The system is a first-order system because the slope of the attenuated gain, which is after the cutoff frequency, has a slope of -20 decibels per decade. If it was a second-order system, the slope would be -40 decibels per decade. The frequency domain analysis is useful because it allows us to see the relationship between input frequency and output gain. By using this frequency domain, we are able to identify the cutoff frequency of our system. This is not possible to do in the time domain analysis and is important because after the cutoff frequency, the gain will begin to decrease very rapidly, which limits the amount of usable frequencies for our system. Here we can see the difference between our experimental results and the theoretical Bode plot. The theoretical Bode plot was generated using values for Km and Tm that were found previously from the experimental Bode plot. It is clear that the results for the gains closely resemble each other, but the phase lags show large differences. After analysis of the frequency domain results, we found that the cutoff frequency for this system is around 9.1 radians per second. At frequencies greater than this value, the output gain will be attenuated and lead to performance that isn't optimal. Therefore, looking at the two cases presented in our design problem, where case 1 is a 2.3 volt wave with a frequency of 0.1 Hz, versus case 2, where we have a 3.5 volt wave with a frequency of 15 Hz, it is clear that case 1 is the preferred case for optimal performance. From a voltage standpoint, both voltages are within the linear regime, so we must analyze the frequencies of these two cases. Since case 2 has a frequency greater than our cutoff frequency, the gain of the input will be much less than 1, or less than 20 decibels. Additionally, the phase lag of an input of 15 Hz is nearly 90 degrees, meaning that the motor response will lag far behind the input. The combination of the attenuated gain and large phase lag means that the model will not be able to provide an accurate representation for the motor response for case 2. Thank you for watching. Are there any questions?